All right, everyone. So welcome back to our next unit. Our next unit is basically what we've been building up to. So everything since day one has been leading up to this. To see how that's happening, let's go ahead and just quickly review what a random variable was. So in the previous section, we focused on experiments, and experiments essentially meant that from that experiment, I was interested in some kind of outcome. And the experiment basically said that when you quantify that outcome, for example, the number of individuals that are at a bus stop, that could be a random variable. Somebody's height 5 years from now is a random variable. So again, it's experiments that give rise to a quantitative value. Even if we're looking for example, how many individuals are going to agree with a certain statement, that's qualitative, but we make that quantitative by asking how many individuals will agree with a certain statement. So random variables pretty much what you're interested in determining, but whose value is random. So again, it's just a variable, but it's something that's random because you can only determine its value by sampling or by conducting some kind of experiment. In the previous section, we essentially studied two kinds of random variables, and those were the discrete and continuous. So discrete random variables were the random variables that result in whole values. For example, x equals 0, x equals 1, x equals 2, and so on. And that's why they were called discrete. We did go ahead and see that a very important distribution was the binomial distribution. And the main takeaway is that it's a named distribution. There's a name associated with it. And that's really important because in essence, it says that we can determine all there is to know about this random variable, aka an experiment, by simply looking at the binomial distribution. There is a formula for it, which luckily for us, we're not going to use because we're simply going to say the fact that a random variable is known to be binomial with parameters n and p. So the parameter is basically the important value that will help you in essentially determining anything you want about a random variable x. So we can see that if you know n and p, you can find any probability in an experiment. So you can find the probability that x is any given value by simply using StatCrunch, because it allows us to find probabilities. We can also ask what is the expected value of our random variable, which we simply called mu of x, which says that what value can we expect to see over repeated trials. Now, there are more named random variables. There's many of them. So one is, for example, a geometric random variable. And so geometric is related to binomial because it's the exact same thing, except you don't have a sample size that's given. You just simply keep trying to do something until you have your first success, right? Or person responding with a yes. So that is a discrete random variable. The fact that it's a named random variable means that we know everything there is to know about it by simply knowing the value of its parameter. So the parameter in that case is p. One that we did not look at was a Poisson random variable. And that one basically counts how many times an event is going to occur in a given interval. Similarly, there's a formula for it, so we're not worried about that because we're simply going to go to stats. Calculator, and we select the relevant calculator that we need. And that's simply the name of the random of the distribution that the random variable follows. That in essence is how we handled discrete random variables. Then we also switched on over to continuous random variables. So for example, if there's an equal chance of something occurring, think of time. Time is measured, time until something occurs, you got to measure it, so therefore that's continuous. So if your random variable is continuous, this would follow a uniform distribution. And similarly, we can see that the only values we need are A and B, where A is the smallest time that something could occur, and B is the largest time that something could occur. The main focus for us in our previous section was the normal distribution. And every time we drew a normal distribution, we only needed to provide the center and the spread. And so this again tells me that mu and sigma, it should actually be sigma squared, are the only parameters that we need. Okay. So let's summarize what we just said. In previous sections, if we knew the behavior of some kind of experiment, we were able to say that the random variable of interest was a special kind of random variable, that there was a formula that already existed and has been studied extensively in the past, and therefore we can find the probabilities and expectations very easily. And this is what you want to take away from that. If something is a named random variable, if a variable of interest is a named random variable, then you basically know all there is to know about it. And all you need is the value of its parameter. So we're going to build on this. So 4.1 is called sampling distributions. So let's go ahead and just preview what this unit is about. In this unit, we're going to be using named distributions, which means distributions that have been studied. And so we can find most anything that we want about our random variable. But the way that we're going to do this is we're going to say, let's understand how our sample behaves. So we want to understand the probability, the likelihood that when you take a random sample, so SRS, what is the probability of obtaining this kind of sample? Because from a sample, we're going to obtain statistics. Now, if you can understand how likely a statistic is, then that allows you to cross this, the bridge here, where we go from our sample to being able to say something about the population parameter. And remember, we never really observed a parameter. Going from a population to computing the parameter, this was a prohibitive endeavor because it was very time consuming or would be very expensive or not possible at all to examine every individual in a population. So right now, we're essentially going to cover what is necessary to cross this last bridge, where we go from being able to say, here is my sample, here's my sample statistic, what can we say about the parameter? So for example, X bar or P hat. How does that tie into the population mean or the population proportion? Whenever you go from a statistic to a parameter, you're doing what's called inference. And inference is the last big part of statistic that we're going to deal with. So let me give you some ideas of what we're going to compute. So something I can ask is, given the sample, statistic, so think of either one of these, X bar or P hat, we're going to be able to answer questions like, number one, what do we believe is the population parameter? What is the most likely value of the population parameter? Number two, what values, even if you can't tell me what value you want, we can say what values could the population parameter be between? So this is called an interval. So Item number one, what is the population parameter? That's called an estimate. Item number two, what is the value that the population parameter could be between? That's going to give us an interval. So again, we're crossing this bridge from our sample to the population. And we're going to be able to give an estimate of what these things are. We're going to be able to give an interval that we believe will contain the population parameter. We're also going to be able to determine the sample size required to meet certain conditions. And so that has to do a lot with polling. But the last major thing that we're going to look at is we're going to look at, so given the sample, is there evidence? Does the sample support a claim? Regarding the population parameter. And so that's called a hypothesis test. So these are the three main things that we're going to spend the rest of the course performing. And that is going from our statistic to being able to say something about the parameter solely based on our sample statistics. And that's a very delicate balance, because in order for us to be able to cross this bridge, what we need to do, the very first step, is to ask, how do random samples behave? So if we start with a population, we first got to understand the question, how do the sample statistics behave? So let's go ahead and take a random sample, SRS, easiest way. We obtain a sample, which is a smaller representation of the population, and then we're going to compute the sample mean or the sample proportion. In reality, you could compute any statistic. These are the two main statistics we're going to focus on. And notice that the question is, how do random samples from the population behave? So we need to understand the behavior of these sample statistics. And we've already attempted to do this. We attempted to do this at the very beginning of class when we asked, how do different samples or sampling techniques affect our sample statistic? But now we have the terminology to actually answer the question. Because now we're asking, if I take a random sample, compute the mean, this mean is my random variable. It's the variable of interest, and I need to actually take a sample to determine what that value is. If you do this over and over again, we hope that there is going to be some kind of behavior for this random variable that will allow us to do essentially describe how this is going to behave. And the reason why I started with this review of random variables is, as we will see, the sample mean and sample proportion are very closely related to the normal distribution. All right, so hopefully you have an idea of what the rest of the class is going to entail and are kind of excited on what's going to happen, because we're going to be using everything we've learned to now describe the sample mean and sample proportion. So our first question is, what is the distribution of the sample means or sample proportions? And this one question is what allows us to then finally cross this boundary from sample to population. And it's surprisingly simple, as we'll find out in the first section of this unit. So we've reviewed what inference is. Please rewatch the video if you missed it. So inference, remember, is jumping from sample to population. And I gave a few examples on what kind of inference we will be performing. So review the video if you missed it, because you are going to want to answer the question in Canvas. And what we'll do next time is we will be able to answer this question: what is the distribution of the sample statistics?